Hello and welcome. Today we're diving into a piece of tech that honestly sounds like it was pulled straight from a sci-fi movie, superconducting magnetic energy storage. We're going to find out if this could really be the perfect battery that we've all been dreaming about. But first, let me ask you something. What if you could charge a battery in the blink of an eye? And not just do it once, but do it over and over and over again, an infinite number of times, without it ever wearing out? And what if you lost almost no energy in the process? It sounds totally impossible, I know, but that is the incredible promise of the technology we are digging into today. So to really get why this is such a potential game changer, we first have to talk about a huge fundamental problem that our modern world is facing. Our power grid is terrible at storing energy. I mean, think about it. Our whole lives run on electricity, right? But here's the crazy part. We have almost no good way to save it for later. This becomes a massive headache when you start talking about renewables like wind and solar. They're amazing, but they don't work 24/7. So we desperately need a way to, bottle that sunshine and wind for when it's dark and still. And this is where our story takes a really exciting turn. There's a potential solution that's just on a completely different planet from the normal batteries in our phones and cars. So let's take a look at what some people are calling a near-perfect battery. So what in the world is SMES? Well, at its heart, it's a system that doesn't store energy with chemicals. Instead, it holds it directly in a magnetic field. It pulls this off by zapping a huge electric current through a massive coil of superconducting wire that's kept ridiculously cold. And once that energy is in the magnetic field, it can just hang out there, pretty much forever. Okay, now this is where it gets really mind-blowing. Let's just compare SMHS to something we all get, a lithium-ion battery. The numbers are just staggering. An efficiency of over 95%. But look at cycle life, unlimited. Think about that for a second. It never wears out. You can charge it and discharge it forever. That means no e-waste problem. The response time, instant. And maybe the craziest stat of all, zero self-discharge. You charge it up and it just stays charged. It doesn't slowly leak power like every other battery we know. Let's just park on this number for a moment. Over 95% round-trip efficiency. That means for every 100 watts of power you put in, you get more than 95 back out. That is just incredible. When it comes to energy storage, it's pretty much a lossless electrical spring. The energy just bounces right back. And here's another beautiful thing about it. Unlike other big grid-scale storage methods, nothing in a SMES system actually moves. There are no turbines to spin or pumps to run. Because there are no moving parts, these things are incredibly reliable and don't need a lot of maintenance. Okay, so it sounds amazing on paper, but how does it actually work? I mean, how do you literally trap electricity inside a magnetic field? Well, let's break it down. It really boils down to three main pieces. First up, you've got the heart of the whole thing, the superconducting coil. This is where all the magic happens and the energy is stored. Second, you have the power conditioning system. Think of this as the brains of the operation. It takes AC power from the grid, turns it into DC to charge up the coil, and then flips the process to send that power back out. And finally, the cryogenic refrigerator. This is basically the life support system, keeping that coil super, super cold so it can do its job with zero electrical resistance. Now, that big coil can be designed in two main shapes. You've got the solenoid, which is just your basic tube or cylinder shape, and the toroid, which is shaped like a donut. The solenoid is way simpler and cheaper to make, but it leaks a massive magnetic field everywhere. The toroid, on the other hand, is much harder to build, but it cleverly keeps that magnetic field contained inside itself. And that's absolutely crucial when you start building these things at a large scale. This might all sound like something that only exists in a laboratory, but SMES technology is already out there in the world, quietly doing some really critical jobs. Let's take a look at a few examples. So right now, you can find SMES units in places where the quality of the power has to be absolutely perfect, like in microchip factories where even a tiny power flicker can destroy millions of dollars worth of chips. They're also being used by utility companies to stabilize weak spots in the power grid. There's one in northern Wisconsin that helps a paper mill from crashing the local grid. Plus, they can work as gigantic instant-on backup power supplies, and are even being tested for wild stuff like electromagnetic launchers. Okay, so if this tech is so great, it's almost perfect. Why isn't it everywhere? Well, you probably saw this coming. There's a catch. A really, really big one. Let's talk about the high price of this power. This chart really tells the whole story in a single glance. Yeah, the refrigeration system costs money, sure, but the cost is just completely dominated by one thing: the superconducting material itself. That special wire you need to build the giant coil is, by a huge margin, the single biggest reason these things are so expensive. Now, here's something that feels totally backwards. You'd think that high-temperature superconductors would be cheaper, right? Because you don't have to cool them down quite as much. But nope. The problem is that the current high-temp materials can't carry as much electricity as their super-cold cousins. So, to store the same amount of power, you need way, way more wire. And all that extra material makes the whole system 2 to 4 times more expensive. It's a really weird trade-off. And the problems don't just stop with the cost. I mean, we're talking about some serious engineering challenges here. To store enough power for a city, you'd need a coil that's hundreds of meters wide. The materials themselves are often brittle ceramics, which are a nightmare to make into long, flexible wires. It can take up to 4 months just to cool one of these giant systems down. And finally, that powerful magnetic field creates these immense physical forces that are constantly trying to rip the coil apart. But, even with all these massive hurdles, the potential here is just so incredible that researchers are working like crazy to solve these problems. So, what does the future hold for this kind of technology? In the end, it all comes down to material science. The absolute holy grail here is a breakthrough, a new kind of superconductor that works at warmer temperatures, can carry way more current, and, crucially, can be made easily and cheaply. If someone cracks that nut, it wouldn't just make SMES better, it would completely rewrite the rules for energy storage. And that really brings us back to the big question, doesn't it? SMEs offers us something that is tantalizingly close to a perfect way to store energy. It's fast, it's efficient, and it lasts forever. But the cost and the engineering challenges are just enormous. So as we think about the future, we really have to ask ourselves, is the perfect battery worth the price? Something to chew on. Thanks for joining me.